Welcome to the 2016 NASA Ames Summer Series. When Robert C. Hooke in 1653 took a thin slice of cork and observed it under a microscope, he discovered modular chambers he termed cells. Upon further studies, we found that living cells have the capability to react and adapt to the environment. Imagine a world where vehicles start off with a particular form and have the capability to morph during travel to the environment that they experience. Today's seminar, entitled Building Blocks for Aerostructures, will be given by Dr. Cheung. Dr. Cheung received a Bachelor's of Arts from Cornell University, then came over to this side and received a Master's in Computer Science. Actually didn't, sorry, apologize. Stayed at MIT. Did a Master's in Computer Science at MIT, followed by a PhD in Applied Physics. He joined Ames and is currently a research scientist with the Office of the Chief Technologist, and he conducts research on the application of building blocks-based materials and algorithms for aeronautical and space systems. Please join me in welcoming Dr. Cheung.
Thank you, and thank you all for coming today. I'd like to begin by acknowledging the various contributing organizations to the work that you'll see in this talk. In particular, the Aero Research Mission Directorate's Convergent Aeronautics Solutions Program, which is right now our biggest sponsor, if you will, under the Transformative Aeronautics Concepts Program. That work extends from NASA Aeronautics Research Institute Team Seedling. That was very enabling. And we also have some work that you'll see today that's been funded under the Space Tech Mission Directorate's Game Changing Development Program. Also involved are with in-kind support as well as just as collaborators are UCSC, the Massachusetts Institute of Technology Center for Bits and Atoms, and Moog Space Systems. I also want to acknowledge the two most significant mentors I've had here at Ames in the short period of time I've been here so far, which is Harry Partridge and Sean Sway. And Sean Sway has also spent time sitting in the lab, as well as all the faces that you see here, which are the minds and hands behind the work that you'll see in this presentation. And being here at NASA Ames Research Center has been really wonderful. You can see this is just some of all of the people here who have been involved in this work, and it hasn't been going on that long here. So you get an idea of the kind of support that we have here at NASA Ames. So thank you all. So I'm here today to talk about building blocks for aerostructures, and this comes from an intersection of digital materials, cellular solids, and fiber composites. And so what I aim to show is that it's possible to make things lighter, in a way stronger, as well as possibly faster and cheaper by assembling composite materials from small, discrete parts. So short-term applications include infrastructure like buildings and bridges, or vehicles like airplanes. In all cases, the most significant benefit might be in material life cycles. So the most obvious short-term benefit comes from the reduced weight. For example, less structural weight in an aircraft means less required fuel, which itself means less weight, which means lower structural requirements and even less required fuel. So I'll say a bit about each of these areas and then explain how it all fits together and show a couple of examples that we're pursuing as applications. So what are digital materials? Digital materials are made from a small and discrete set of parts with discrete locations and discrete connections. They promise low cost and reversible ways of making things with low precision assembly requirements. Think about the precision of a 3-year-old relative to the precision of the assemblies that he or she can make from, say, Lego bricks. So this is accomplished with error reduction, tolerance, and correction mechanisms, which is just like what we see in digital communication and computation systems. So digital systems in general, as we understand them, employ many, and as we've engineered them, employ many fungible units to form assemblies with a wide range of size and function, all from low and finite sets of types of discrete building blocks. If the application of this to materials sounds to you a bit like biology, and Jacob helped to introduce this analogy, that's because it is indeed similar to our basic models for how materials are used in living organisms. So in biology, we see discrete assembly resulting in structures with a wide range of size and function, in organisms as a whole, or specialized organs and tissues, all from a low and finite set of types of discrete building blocks. So the simplest way you can look at this is amino acids as building blocks. And so the diversity of things that can be made with this sort of combinatorial system at various levels of hierarchy is plainly evident. And the small number of required building blocks along with system scalability has allowed synthetic biologists to make new systems from the same or similar material. It's amazing work with incredible rates of progress, some of which is going on here. For many of our current manufacturing applications, however, we may be able to take advantage of the ability to work at a much larger scale and with many fewer building block types or diversity of parameters and objective functions. So short of setting out to try and recreate life, which is being done in the synthetic biology world right now, we're looking at modular systems that on the surface appear not that different from those that have been studied for ages. But historically, these kinds of physical systems are often considered to be a mechanical compromise relative to conventional manufacturing methods. So there's a couple things I want to point out on this slide. The first is that while it's sad that the Lego house got torn down, it's not sad that most of the parts got distributed amongst many children and therefore maintain most of their utility. It's harder to do that with your typical demolition job. So can I have a show of hands for how many of you played with toy sets like that? Yeah, pretty good. And so can I now have a show of hands for how many of you, given a set like the one in the middle, would only use the provided bricks to make the things shown on the cover of the box? So in a way, that set for a wind turbine set is very realistic because it comes with the truck that is almost as big as the turbine. And today's terrestrial wind turbines are indeed size constrained by that truck, which is in turn constrained by the geometry of the roadway system. So we have wind turbines that are set by the roadways. So the funny thing is that the Lego version doesn't actually need the enormous truck. And you can bet that there are some kids that have made some curiously big wind turbines together with mysteriously small trucks, just like how the parts are meant to be exchanged among the 100 or so explicit designs in the reconfigurable plane sets. Okay? So one of the things that makes toys like this work so well is that the parts fit together into a regular lattice. And when it comes to studying the mechanics of lattice structures, we have the science of cellular solids. And so this was forged in the 80s by Lorna Gibson and Michael Ashby, and it shows that we can treat these kinds of materials as continuous materials with bulk properties. That really changes how you can design with these kinds of materials. And so the result has been the modern engineering use of materials with useful characteristics like lower density, greater elasticity, and better energy absorption than previously commonly used. So these include the foam and bicycle helmets, optimized uses for wood, and ultralight materials like aerogel. So the properties of any cellular solid are defined by the properties of the solid material that it's made from and the geometric spatial configuration of that material. So if we're going to assemble a cellular solid from small parts, we could do whatever we wanted with the spatial configuration. So what should we aim for? To get an idea of what we could try, we can look at a material property chart like those pioneered by Michael Ashby, and this shows most of the broad categories of materials that we use in engineering today. It has density along the x-axis and modulus or stiffness along the y-axis. So metals and ceramics are the densest and stiffest, and foams are the least dense and least stiff. If we were to make anything out of these materials, it's simple to see what the optimal performance could be by following the proportional modulus to density lines down the chart. So if you build something sparse that optimally uses any of these materials that you see in the bubbles to support the loads with behavior that's dominated by stretching of the material, then the relative stiffness will stay proportional to the relative density. So it's going to follow down along those lines. So this is sort of the absolute best case design goal, a physical boundary, if you will. So we therefore know that we should be able to access the area in yellow on this chart by properly making a cellular solid out of a known constituent solid material. So in practice, however, we've only followed these lines down about an order of magnitude and relative density. So we've had reasonable success getting down to around 1/10 the volume of the materials that you see here, most of them, before reaching the limits of conventional manufacturing methods. So of the designs that are truly volumetric periodic structures, a pioneer of lattice-based metallic structures, Hayden Wadley, has said that it is not trivial to ensure that the increased cost of periodic cellular manufacturing processes is compensated for by the reduction in weight. So whatever cost gains you get in your application through the reduction in weight. So this presumably refers to the technologies like the cast aluminum structure that you see in the lower right. So architecture and civil engineering have employed space frame truss structures for a very long time in buildings and aircraft, but have yet to implement the principle in a way that takes advantage of the ability to treat such structures as a continuum material. So in any case, the appreciation for designs that have lots of similar elements sharing structural duties is evident throughout our history of high-performance structures. You think of the Eiffel Tower, or you can think of the geodetic aircraft, the Vickers aircraft from the 30s. So we're still left with the red area on this materials property graph, which is physically possible, but for which we still have yet to show suitable methods of fabrication. So we do have methods of creating cellular materials with greater reductions in mass density than the 1 to 10 that I just mentioned. So these, however, have the property that instead of material stretching, the phenomenon that governs their behavior under load is bending. This results in the bulk following a reduced mechanical property laws, which is shown here. And many of these materials can be produced very efficiently, for instance, by bubbling or mixing a liquid state with air before hardening. So it is these kinds of materials that have achieved ultralight status at the extreme left-hand side of this chart. But this still leaves this entire red region of the chart behind due to the effect of the beam bending dominated behavior and the order of magnitude practical limit for the processes that produce materials with proportional scaling. So it's this region of material property space that we've focused on with some success. So it's interesting because for many applications, it's not just strength or stiffness that matters or weight that matters. It's strength or stiffness per weight. So you can make something with the same stiffness per weight but at a lower weight, then it costs less to do things like move it around, keep it steady, heat it up, or cool it down. So one current industry strategy for trying to get total systems into this regime is with fiber composites, which as a technology is undergoing a bit of a renaissance in prototyping capabilities and extensibility of manufacturing equipment. So here we traditionally have a process where the manufacturing systems are larger and more complex than the product, which can be a problem when your product is as large and complex as a passenger aircraft. So this diagram is from a guide that does an admirable job of distilling best practices for composites material design, analysis, and manufacturing, as well as testing, into a concise 693-page handbook. Commercial aircraft are used as examples in this guide, and new composite aircraft architecture can be partly considered as attempts to reduce the enormity of this pyramid of design, analysis, and testing. So for example, we now have the cockpit and forward fuselage down behind the 9th passenger window, all the way from basically the nose to behind the 9th passenger window, as a single piece. manufactured as a single monolithic carbon fiber winding. So this one part is about 1/6 the size of the entire plane. It needs a tool or formwork that's about 1/3 the size of the entire plane, which needs to go into an autoclave to cure the composite that's almost the size of the plane, and then get processed on a CNC mill that is also almost the size of the plane. When it comes to shipping the part to the final assembly plant, it has to go on a plane that's twice the size of a plane. This plane was custom designed and built as part of the manufacturing process for another plane. So this isn't particularly scalable. By the way, it's not only one manufacturer has done this, and this isn't the first time in history this has been done. But it isn't particularly scalable, though they've done an admirable job up to this point, but it's largely in the name of lighter weight. So what digital composites propose is to assemble structures from a lot of linked parts. The core concept is that if we can effectively couple loops of fibers, then a chain of discrete fiber composite parts can be close to the strength of a monolithic part and would have advantages with manufacturing processes, serviceability, and reusability, in addition to the tunability and extensibility that are general goals of digital materials. And the tunability in particular is also a very specific goal of composites. And so at this sort of larger scale than amino acids, of course, recent work has shown that a building block approach can be used to achieve novel material properties in cellular materials with centimeter scale lattice pitch. So these are essentially three-dimensional optimized fiber composites. You get the unidirectional material performance scaling, but now in a quasi-isotropic cellular solid. So we've shown better specific modulus scaling than previously known ultralight materials, and this is possible because assembly allows us to produce geometries that have not been achieved with conventional ultralight processes. So the strength of the material performs similarly to the expectations of other high-performance ultralight materials, and the stiffness is much better. So despite how light it is, you don't need much of this stuff to, for instance, support the weight of a person. And you'll see some application slides that demonstrate that. But we're not just interested in quasi-static applications here. There are many metrics that we can use to compare the usefulness of this material to what we use today. And a simple example is a beam performance index, first described by Ashby and Saban, which simply quantifies beam bending stiffness. So for a given description of a beam, a given cross-sectional mass distribution or second moment of inertia, this is governed by the square root of the material modulus divided by the mass density of the material. So we can immediately recognize that exceeding the quadratic relative density to relative modulus of cellular solid scaling will have a very positive effect on beam performance. So by reducing the weight for these very specific performance metrics, we don't have to maintain ideal performance as long as we don't go below the quadratic scaling to actually increase the functional performance in an application, even for one as simple as a beam. So here we see that we've achieved in experiment a better performance than conventional aerostructure materials. So this is based on the linear elastic regime, which is generally considered to be the useful bit. And when you exceed the linear elastic regime, we do see a non-dissipative superelastic mode. And so this, I won't go too much into detail here, but what you see is there's this effect of twisting the free end nodes, transferring a substantial bending moment through these nodes, and you'll see from the strut spacing and the buckling of the struts that you have this coordinated twisting motion. And so throughout a large structure, this appears to develop into a coordinated buckling behavior that is something like a three-dimensional folding or pleating. This is also readily apparent in simulation work being done by Kahn and Joseph. And the rotational displacements that develop for each node are antisymmetric relative to most of its neighbors. A kind of unconstrained coordinated twisting stress response has been reported in two-dimensional surfaces, particularly some natural ones. And we're currently working to describe this for such a partially constrained condition in three-dimensional lattices. So now what happens if we keep loading the material past this point? A significant perceived pain point with fiber composites is with failure modes of typical engineered parts. A caricature of the stress-strain curve for a typical fiber composite part is a straight linear elastic line that abruptly ends in breakage. And what this means in a practical sense is that breakages can be accompanied by elastic unloading of a great deal of stored energy. And this can be quite dangerous. So now we still have a great deal of work to do on this topic of failure mechanisms for digital composites. But early tests suggest the possibility of being able to tune materials to behave in new ways. So this is an open frontier in material science. So why does this work? So it's possible that we have mechanics at work that can be described as stretch-bend coupling. And this has been described not so much in the bulk material solids literature, but once there is any tendency towards microstructural bending under load for the kinds of materials that have been considered in the class of stochastic materials in the cellular solids literature, it seems that the geometries that result from the typical ways of making engineered foams, stochastic engineered foams, predispose the structure to fall into a bending-dominated behavior. So we don't really see this middle regime in most of engineered cellular solids. There just doesn't appear to be much observable middle ground. In contrast, studies of biomaterials such as intracellular meshworks of actin, microtubules, and extracellular matrices of fibrin and collagen have shown mechanical performance that exceeds predictions based on framework rigidity theory. So these are the same theories that underpin the cellular solids work. And they use these rigidity criteria as bases for estimating the balance of degrees of freedom and constraints in a structure. So recent work suggests that departing from these principles by assuming that significant bending moments can be transmitted through the nodes in the structure can result in effective models of these biomaterials. So we think, well, many support this model for its simplicity with an understanding of the relative magnitude of the forces concerned when you're talking about biomaterials. And if in principle this kind of framework exists, then we should be able to create one at the macro scale, and it looks like we have. The level of description that's being used for the biomaterials actually suits what we're doing perhaps even better. So if we apply a simple adjustment to the dimensional scaling arguments that so efficiently describe classical cellular solids, we produce a scaling rule for stretch-bend coupled lattices that's very close to the behavior that we actually see. And so we have these different lattice types that we've essentially been playing with building blocks that we produce. We snap them together initially by hand. And we have these different types of geometries that we're working with. There's nothing magical about any one of these particular geometries. There's just ones that work and ones that we can get to work together. And so we can ask the question of what happens if we start mixing them. And so to illustrate the sort of exponential fan-out and variability that you can get by doing this, this is an example of designer material properties from this approach. So each of these towers are built with the same set of components, but compress or buckle in different ways under identical boundary conditions, all as a result of differences in the ordering or spatial arrangement of the parts. So this becomes a jumping off point for us as an example of bringing it down to an application that utilizes the variability that you get as you mix these parts. So the key thing to understand here is that there's this global variability that we can produce by mixing a very small set of different types of parts, as long as we have a lot of them. And so it's exponential. The behaviors that we get that we can get are exponential with the number of parts that compose our system. So the first example is wings. If I can get this to play. And so this shows, with the same models of the large lattices that I just showed, what kinds of deformations can be produced by simple actuators with just specified arrangement of stiffer and less stiff parts in a structure. And so we did some initial testing of different kinds of shapes, going between different kinds of shapes, and seeing if, in principle, they could hold up, for instance, in a wind tunnel. And the results looked promising enough that we went forward with the NARI Team Seedling project, which basically takes the pyramid of test and takes out the middle. So the top of the pyramid of tests are the small coupon tests, and our parts look like those small coupons. And so we can go very quickly as far as the entire process from design and manufacturing, from those small coupon tests to a complete structure with apparently complex behavior. And so this shows the process including some testing of our the skin structure. That was on campus, by the way. And so we can go through, and the skins are also discrete units. And so this obeys the same sort of property of what we can do in terms of the design and testing, and very quickly get to the wind tunnel model that you see here. And in fact, we had two. And we have the parts for another one. And so you see the bench testing that we've done to validate the behavior and the stiffness of the structure. And we've been able to bring the modeling down in the same way. So here we're looking at vibrational modes using a modeling strategy that actually obeys the same kind of principles as our fabrication strategy. And so what I mean by this is that a traditional finite element model will break down the geometry into a number of finite elements that compose your mesh. And what we've been able to show is that we can have a number of different mesh element types that equals the number of different parts that we have. And we can model and exhaustively test to tune the model of those individual parts. And then each one of those is a single simplex in the mesh for a simulation. And that allows us to do things in terms of the simulation and design essentially in real time and with computational loads that vastly undercut traditional processes. And so all of this work in the wind tunnel test that you just saw videos of led up to a direct comparison between the white 3D printed model you see on the bottom. It's not a biplane. They're just stacked on top of each other. And the twist model on top. And you can see on the bottom model that we have conventional ailerons that are replaceable on the bottom model. The bottom model, by the way, was 3D printed by Gary Wainwright at Langley. And so we were able to do a direct comparison between these two and show the viability of the digital composite structure. So as opposed to a traditional wind tunnel model that is often built extremely stiff, sometimes out of a solid block of metal, we were able to use a structure that, in this case, weighs 100 grams on each side. And we had some fun with the wind tunnel tests. Here, we're driving it with a forced oscillation and also driving the wings to actually counter the motion of the forced oscillation of the wind tunnel rig. So this is the team, including the flight dynamics group at Langley, that was wonderful to work with. And so we moved forward with 100 grams per wing and surviving to full pressure of the wind tunnel that we used. We thought, why not fly it? And so we took the same wings and flew them. There was sound, but you can imagine the sound that this makes. And that's a barrel roll. Thanks to a very skilled pilot. And so what we're going forward with for this project, which is the Mission Adapted Digital Composite Aerostructures Technologies Project, or MADCAT for short, are what we're calling X to the N planes. And so you can see that if we have this set of building blocks that we can show can rapidly be integrated into a flying aircraft, and we can take that same set of building blocks and just by snapping them apart and snapping them back together again in a different configuration, meet very rapidly through design and analysis all of the goals of aircraft design analysis and manufacturing. That means that we can very quickly get into the air lots of different, maybe novel, maybe theorized in the literature, but difficult to fabricate aircraft types, including in particular the morphing aircraft types. Because what we've been able to show is the ability to change where a stiffer part and a less stiff part is throughout the structure in order to define global deformation modes with very simple actuation. There were only 2 servos on the twist wing that I just showed. And we think we can keep the number of actuators extremely low for essentially arbitrarily complex deformation modes where the number of states relates to the number of actuators, not the complexity of the deformation mode. And the manufacturing techniques that we look to employ with these methods and that we're going forward with are ones that suit mass manufacturing, which means that the cost of all of the components can come very close to the theoretical energy cost of those components. And the long-term vision, if you have a material ecosystem that works this way, is the ability to take that fundamental energy cost and amortize it over many different applications. Because the actual cost of assembling these things by snapping them together is extremely, extremely low. And so you can start to envision completely new ways of managing material. So this brings us to this question I've brought this to this question of price performance. And so to put this in perspective, we can briefly look at how this proposal relates to aerostructures fabrication as we know it. And so the closest example of an aerostructure built with the principle of distributing load requirements over many smaller parts is probably the Vickers geodetic aircraft. So one of them is a plane that still holds the record for distance flown nonstop by a single engine aircraft, so over 7,000 miles. So we can assume that this was not a heavy aircraft, obviously. So it also had the reputation for being extraordinarily damage tolerant, and the unusual robustness came at a perceived cost of manufacturability. And the factory countered this perception with a much publicized exercise where they built an entire aircraft from start to finish in 24 hours, actually taking off after that much time. There's not a lot of information out there on how many parts are in those aircraft, but the time of production is similar to today's commercial production capability for, say, a Boeing 737. So the current 737 fuselage is comprised of a couple of 100,000 parts, an additional couple 100,000 fasteners, rivets, are used to attach these parts to each other. With a factory system of about 700 people, about 1 fuselage per day is completed. And therefore, we can estimate that on average, 7,000 parts are added to the assembly per hour, or 10 per person per hour, or about 2 per second. And estimating the total structural volume of the fuselage as a cylinder, 4 meters in diameter, 40 meters long, 25 centimeters thick, gives us about 120 cubic meters. And this would require about 900,000 parts if we simply use the Q-Box truss digital composite design presented earlier. So I know that trained students can place one of the Q-Box truss parts every 5 minutes or faster. So with the same workforce, the job will get done in about 5 days. So we're not even talking about a necessarily great increase in parts to realize some of the advantages of digital construction. And the difference here is that for an entire plane, we would now have a few million of the same part instead of around 1 million of custom parts with around 1 million of the same rivet. So the life cycle implications are not trivial, from design through fabrication to repair and reuse. It's easy to see the potential advantages. So this points out that your typical toy building block price per kilogram comes very close to what you would expect for the cost to produce the raw material that it's composed of. And the next vertical line over are the materials that we're currently using for our experiments. And we can expect to come reasonably close to that cost at scale for producing arbitrarily large structures per kilogram. And so that's compared against things like tennis rackets and bicycles, consumer drones, which I'm not sure why they're that expensive, except that maybe that's what you all will pay for them. And then we have the newest composite aircraft and your phones, which actually cost more per unit kilogram, but at least looks less than an orbital launch, except when you consider what SpaceX seems to be able to do, which is actually just under what your phone costs per kilogram. And so we can look at what this means for space applications, where this can not only change how you get to space, but what you do once you get there. And so what does it mean to be building things in space, and what does it do for you? And so the launch environment, many of you know, almost always presents the largest and governing structural requirement for a spacecraft. And so using dimensional scaling arguments and the difference between the launch environment and, say, space station deployment for an assembled CubeSat, you could see a factor of 10 difference in the low-frequency accelerations, which can theoretically result in about a factor of 3 reduction in the required structural mass. And so this is even more pronounced when you're considering launch vibration. Given the typical strategy for avoiding vibration-induced damage by keeping natural resonant frequencies higher than the significant driving frequencies during launch. And so for these same CubeSats, this could theoretically mean a 100-fold or more decrease in the required structural mass, depending on what you need to carry. So that's a pretty big deal. And the state-of-the-art energy to low Earth orbit right now, and that is based on the Falcon 9. The gap between that and what we know is the minimum theoretical energy if you were, say, reusing all of your launch mass, not including the fuel, is quite large and actually spans the space of the production energy per unit kilogram of a lot of the materials that we use in space, or in engineered materials in general. Which means as we come down this chart with the right-hand line, it starts to become much more sensible to be not only building and doing manufacturing in space in general, but to be looking for the materials to do so as well. So complete raw manufacturing in space. And so this is something that's a lot of progress has been made on since the 80s. And we can leverage the progress, amazing progress done by NASA to look forward to what this means when we know that we can now create these bulk materials, the cellular solids out of composite materials, and now using potentially a much smaller building block and taking advantage of all of the advances in robotics since then. And so here the building block is what you see on the left, which itself is composed of building blocks, smaller building blocks. And they're injection molded fiber composites, and the tubes are pultruded carbon fiber. And these can be assembled into these structures, which we can evaluate on a load testing machine or by standing on them. And so the bridge that you see below weighs 18 kilograms, and we fit it into 2 backpacks and assembled it in a day. And then we disassembled it and made it into a boat. And disassembled it again and made it into a structure. And so some proof that it's not that heavy. And this is the structure, the small habitat structure that we built. And so the fungibility of these units actually extends beyond mechanical systems. And so we've also been exploring what it means to combine the electrical systems, the power systems, and the communication systems, whatever protocols for actually running a mission on board a spacecraft. This is largely Daniel and Greenfield's work, sitting in front here as well. And so this has a name for the larger project, which is Aerostructures. And Daniel would be happy to discuss that name with you. And the Aerostructures board is one of these white boards, and each one can carry a payload. And what you see here includes a comms payload on the one on the right, and actually an experimental payload on the one on the left. And so these boards can all communicate with each other, not only share information, but share power. And so they can each handle power production with solar panels and power storage. And they're reconfigurable into different layouts. So we were lucky enough to be able to work with Marcus Murbach on to get a flight. And the space that we were given was the shape of this instead of the shape of this. So we just reconfigured it and flew that on board a sounding rocket. So there's obviously no underestimating what things you can learn from an actual flight experiment. And so going forward with that, this version shows the interconnectivity extending out not just to a cube, but in 3 dimensions to fill a volume. And so where do we go from here? And so this is the direction that we're trying to head in. And what we think is that this is critical to getting here. So these are much larger structures than anything we've built in space. In fact, there are many orders of magnitude more mass than everything we've put into space combined. But there's no physical principle saying that these aren't possible. It's just that our current methods for producing space hardware don't suit. And so what does it mean to have something, to have a system that doesn't require your factory to be larger than the thing that you're making? And so we think that we may be able to make progress in this direction. And if this seems far-fetched, I like the example of the brick moon, which is a short story by Edward Everett Hale, published in 1869, which is said to be the first historical proposal for a satellite. And the story goes that it was an accident that people were still on the brick moon before it got sent up, and they started a colony up there. And this was completely fanciful in 1869. That wasn't that long ago. So I want to leave plenty of time for questions. So I'm going to leave it at that and open it up to questions.
If you have a question, please raise your hand and wait for the microphone and ask a single question at a time. Thanks.
Okay, so imagine you're on a space mission and you need to have the ability to make repairs and do maintenance. And so there's the philosophy of, or an approach of carrying a lot of the modular parts, which are nearly all identical, like you described, or you could be even more fundamental and carry the completely raw materials and and 3D print parts as you need them. And so, have you given some thought about how you allocate resources in those directions?
So it's a very good question, and in particular because we are doing so much work on 3D printing, NASA as a whole, and the state of the art in general. I think there's some question as to how you define 3D printing, and what counts as additive manufacturing. In a way, what we're proposing with snapping together building blocks here is additive manufacturing. So in that sense, it's one and the same. In terms of what we think of as 3D printing, in terms of the 3D printing devices that we see, for instance, in the space shop, one thing you can look at is the energy cost. And so it becomes a question of what your energy sources are. By and large, when you look at the total energy cost to arrive at a piece of hardware, it appears that the majority of that is worked up in the raw materials production. A large proportion of that you can arrive at or estimate just by, for instance, needing to overcome the latent heat of fusion, so needing to liquefy any given material. And since that dominates the production cost, processes that have to reliquefy the material are sort of going to double your base material production cost, or significantly add to it. And so the versatility is undeniable, and it's moving towards of what we now think of as conventional 3D printing. It's moving towards being able to produce well-characterized parts. But as it is, in a situation where you have very strict energy limits, it can be difficult to justify some of the processes that are currently used for 3D printing. And so some of this comes down to a question of whether or not you can even tell the difference. And so this is a question of pixelating a picture, whether or not a digital picture is sufficient versus what you would term an analog picture. At some point when you get down to the molecules, your color molecules in the picture, you could argue that you have a digital picture anyway. And so the only fundamental difference is your conventionally considered digital picture has the pixels on a regular lattice. Right? And so what we found with digital photography and digital images, that there are all of these advantages. You can do compression. You can operate over the actual functional image in terms of the shapes that are on the image with algorithms extremely efficiently. And we think that the same thing applies to three-dimensional systems, where if you're defining three-dimensional systems in terms of voxels, for a given application, there's a minimum resolution that you need, just like with pictures. And as long as you meet that, then there could be all of these advantages to being able to address things in terms of the discrete states. And so I think there are these advantages in terms of scope of the kinds of things you can do if your systems are built in this fundamentally reconfigurable way versus what's right now considered as 3D printing, which sort of compresses a lot of the industrial infrastructure for producing hardware as we know it into a small box, which is amazing and really useful. But the extensibility of the digital approach, I think, is very promising and interesting. So, thanks. Yes.
For the snap-together structures that you've shown, would it be reasonable to eventually have automated assembly and reassembly?
That's an easy one. Yes. And that's what we're working on right now. That's a major focus of our work in the lab right now. Yes. And we're talking about robots that are actually quite simple. You don't need many, many degrees of freedom. But you could have many robots.
Hi. For the structures you were showing, they were composite materials. They weren't separated in discrete layers, but more combined in a marble structure. I was wondering, how is that determined if you were measuring the force loads, or just have a random algorithm that determines how that is made?
So the one where I showed the blue low connectivity structure and then the red denser structure, and then the sort of marbled one, that one was random. But it's a very good question, and it points to the direction that we're headed in at that point, which is to look at how to optimize the distribution. And Holly, I'm not sure if she's here right now, Holly Jackson has done some work on exactly that question of not only the question between the red and the blue ones was sort of if you have a stiffer one and a less stiff one. And the most basic version of that question is, do you have a part or not in that location? And so it readdresses the topological optimization problem within the scope of the finite element tools in a way that takes advantage of our ability to modularize the finite element process as well. So we can look at some of these incredibly computationally intensive topological optimization methods and apply them to something that would have been also an incredibly computationally intensive finite element analysis problem, but we can cut most of the computational intensiveness out of the finite element analysis problem and just focus on the optimization problem. And so that's the crux of the approach to the x to the n planes, in fact. Because what we'd like to be able to do is define the overall boundary shape and the deformation modes, and then really optimize how the parts are placed within that in order to meet that objective. Thanks.
So please join me in thanking Dr. Cheung for an excellent seminar.